or something comes, like I will finally upload the video, right? So not worry too much about that. But you let me know when the connection goes off. Okay. So are there any questions regarding previous classes? Okay. If there are no questions, let's start for today's session then. So we are on lecture 8 now, and
Sir, you're not audible.
this is lecture 8. So we have discussed like curve fitting, and I have asked you like to take finally see the regression in terms of this probabilistic modeling, right? So we have discussed in detail like how to see this parametric form here, probabilistic parametric form. And then I said that we can compose a likelihood function, right? This was a likelihood function that we have taken. I asked you to just go and take a log of it and find out the derivative with respect to W and beta. Has anybody done that? Has anybody done that? Yes or no? Okay, fine. So like if you take a log likelihood of this thing, then you will get this expression, right? So if you get this expression, and I say that you need to maximize with respect to W first. So let's say I want to maximize with respect to W this expression. So here this term is constant with respect to W. This term is also constant with respect to W. The only term that left is that this term, and it is a
Sir,
log
your
like.
slide is it is still showing just the first slide, machine learning lecture 8, and nothing else is being seen.
Maybe it comes right because of the network. Anybody see the second slide here?
We are still on the first slide, sir, as per the presentation.
Yes, sir. Still on the first slide, sir.
Yes, sir.
You can see this curve fitting revisited log likelihood maximized with respect to W and all.
No, sir.
No, sir.
Just a minute.
Now it's visible, sir.
Yes, sir.
Okay, fine. So if you take a log of this likelihood function, you get this expression. And I said that you need, because this expression, this is a log likelihood function, and there are two variables here. One is W and the other is beta. So you need to maximize your log likelihood function with W and beta. So let's maximize this first with respect to W. W is a vector of a parameter, remember. So I want to maximize it with respect to W. So I found out that these two terms, this first, second term, and this third term, they don't have W in it. So if I take a derivative with respect to W, it will give me a 0. So it acts as a constant. So they will not affect anything, right? It is just a constant with respect to W. So I can ignore it for now. The only term that is having W is this first term. And if I see it carefully, there is one scaling term beta here, right? So if I maximize this first term and I replace this beta with 1, so it will not get any effect. For an example, I have this function and I multiply this function with half, right? 0.5. So I get this function. Or if I multiply this function with 2, so I just get a double of it, right? But you see that it is symmetric in terms of like the original function and the maximum which I had in true function. It's still the parameter values will be same for all scaled version, right? So I mean to say in first term, if you replace this beta with 1, you get this expression, right? So you are actually maximizing the result that you want to get, you will get maximizing this expression will be the same. You will be the same when you maximize this expression, right? If I say rather than maximizing, I will minimize by taking the negative of this function, right? If I take the negative of this function and then I minimize it, so this negative will make it a positive, right? So negative, negative, positive. And can anybody tell me what is this looks like?
Cost function.
Mean square.
Yeah, it is a sum of square function, right? It is a sum of squares. So if you remember in our first slides, what we had discussed that when we do linear regression, so we want to minimize the error of the function, right? If we want to minimize the error of a function, this is what we were doing. So we were minimizing this term, and now just I have arrived this same term when I took the path of log likelihood. So I have taken a log likelihood. I found out when I maximize my log likelihood, the result which I get by maximizing the log likelihood will be the same if I minimize the sum of square error, right? You got this point here on the slide? It is important,
Yes.
very important. Okay. So remember that in general, if you are maximizing your log likelihood, you can always create an error function by taking a negative of log likelihood, right? So see, this is the same thing, but it is just a change of perception. One thing you are maximizing it and the other thing you are minimizing it. So in general, we always try to minimize the error, right? We always try to minimize the error. So if somebody asks you to construct some error function, so you always can construct a log likelihood function and take a negative of it. It will always give you an error function. So if you minimize your error, it is nothing but you are maximizing your log likelihood. And if you're maximizing your log likelihood, it means you are maximizing your likelihood, right? And maximizing likelihood will give you some overfitting. It may give you some overfitting parameter, which we will deal later, right? So right now, I just
So,
told you,
hello.
yeah,
Hello. So,
yeah.
can you explain that beta and one thing, like we are replacing beta with one once
Right,
again?
right. It is just a scaled version of a function, right? So beta just act beta here as a constant. So if you multiply some function, let's say you see this function, right? And you multiply
Yep.
this, you multiply this function with 2 now. So this when you multiply this function with 2, this 2 will get cancelled, and it is a scaled version. It is just doubling you are doubling every number for x, you are doubling every number. So symmetrically, if this was your original function, this was your original function and you're doubling every number, so now this is your original, this will be your new scaled version. And if you are taking a half of everything, then this will be your scaled version, but the maximum value will not change, right? Here for every scaled version, whatever the maximum value was for original, this was your original for x, right? So the maximum, it will stay for the all scaled version. So if you are maximizing this function
Okay.
with w,
So, yeah. Yeah. So, like, then we are putting a negative sign too, right? So
no, that is
that's
different
fine.
thing. when
Okay.
the negative is something different. So I have taken two steps. First, I have taken a scaled version, right? First, I have taken a scaled version. So I replace beta with 1. So this is one thing. Then I said, okay, I can maximize this now. It means scaling the, maximizing the scaled version is giving me the same result. Then I said, rather than maximizing the function, you take a negative of this function and minimize it. When you take the minimum negative of this function, it will make this negative as a positive, right? And then
Yes, sir.
now you're minimizing it, and this minimization is nothing but it is a sum of square errors. So I have just proved that log likelihood function is nothing but it will give you the same result when you minimize the sum of square errors, right?
Okay, sir. Got it.
And one more like conclusion you can take from here, that maximizing a log likelihood function is nothing but it will give you a likelihood will give you somewhere the overfitting results, right? Because you remember on that first slide and second slide in the class, I told you when you try minimize your error to 0, it will result into overfitting, right? If you have a very capable model. So it means when you're maximizing your likelihood function, it will also result into overfitting if you're using a capable model, right? So if somebody asks you whether maximizing a log likelihood will result in overfitting, yes, it will result in overfitting, because maximizing log likelihood is nothing but minimizing the sum of square error, and minimizing the sum of square error, we have already seen that it will result into overfitting. Right? This is the main conclusion of the slide, and which is very important. The second thing, if you just if you maximize this log likelihood function with respect to beta, right? So this acts as a constant. You take this term and take a derivative. It is nothing but n by 2, 1 by beta, right? It is 1 by beta because log of, when you take a derivative of log of something, it will be 1 by something. And this term, it will come into a product form. This will come into a product form as it is. So it will be negative of half, right? And it will come as it is, this term. You put it equals to 0. You put it equals to 0. And when you put it equals to 0, you take this term on the other side. And when you solve it for the value of beta, what you will get? You will get this result, right? So it is nothing but you can say that it is a sample variance. So beta will give you 1 upon beta will give you a sample variance of a data. And sample variance is what? It was like when we had used on the previous slides, when we found out like minimizing the sum of square errors was given by this result. And the same expression we are getting when we are taking a derivative with respect to beta, we are getting a sample variance, right? This is what I have just concluded on the slide, that maximizing the log likelihood will result you in the same thing when you are minimizing the sum of square error, and both result into overfitting. Can I conclude this slide now? Can I go to the next?
Sir, sir, did you take derivative? Then you made it 0.
Right. So it is a calculus, right? Very simple calculus in 12th when you have want to.
So like inside one, shouldn't it be 2 into y of x and like that?
You do it, right?
So
So you just do it and then we will talk. So there is no such confusion in it. You just take a pen and paper and just try it. You will get the same result, right? Don't get confused in this, like how to derive it. So
we are actually doing it with respect to w, right? So derivative.
right, first with respect to w and then with respect to beta, right? Here the good part is when I take the with respect to w, I can ignore these terms, right? Where finally I get with some value with respect to w, then that value I will put somewhere again into this expression, right? When I maximize with respect to w, I will get some parameter. That some parameter I am saying that it is wml. Then I put that which is maximizing with that parameter which is maximizing with respect to w. I put this value again into this expression, and then maximize it with respect to beta, right? That's why this WML is coming from this thing, right? This is the solution of this.
Oh, so like maximizing log likelihood and minimizing with respect to W, like you said, we get the same results. But so
Yeah.
one doubt, like why we took doesn't maximum of likelihood will give you the equal result? We took the log, right, for them first.
Right. Log is a monotonically function. It doesn't detract the parameters in the thing. You just take up MATLAB and take any log of the monotic increasing function. Your parameter will
Okay.
not change for the solution. So
Okay.
that has a property of a logarithm. Okay. Anything else? So here, once this thing, when this discussion comes, I want you to put attention here that if I am taking a derivative with respect to W, my all beta terms go away in the original function. So beta will not disturb me anymore because both W and beta are unknown, right? Once I take a derivative with respect to W, beta terms will not be there. So it will not be a problem to find out what is the value of a W, which will maximize this function because beta is not there. So once I get the value of with respect to W, then I put that value into the expression again and then take a derivative with respect to beta. That's why this WML comes here. This WML says that this is the parameter value which is maximizing the function with respect to W. Okay. Can I go to the next slide or any other confusion here?
Sir, are we concluding
Yes, no.
anything about Hello, sir. Am I
About?
audible? About overfitting,
Yeah.
sir.
Sorry?
Sir, are we concluding anything about overfitting here?
Oh yeah, we are concluding something here regarding overfitting. So we are saying that in last lectures we have concluded that minimizing the sum of square error result into a overfitting. You remember that minimizing the sum of square error resulted in overfitting. Then I am
Yes.
saying that maximizing the log likelihood is nothing but minimizing the sum of square error. If they both things are same, then I am saying that maximizing the log likelihood will also result into overfitting. That's what the conclusion is.
Okay, sir. Yeah, got it.
Right? Both things are same. It is just seeing the one thing from the different perspective. That's the only difference that is there.
Yes.
Fine. Okay. So can I move to the next slide now? Fine. So now if I get the result, I have just proved it that maximizing the log likelihood is nothing but it is like minimizing the sum of square error. And let's say now you are getting a result with the likelihood estimation of W and beta. So this ML is nothing but it is saying that the value of W we have found out using maximum likelihood estimation. The value of beta we have found out using maximum likelihood estimation. So we have freezed some value of W and beta. I got some curve now because the W and beta was the one who was deciding the curve and uncertainty, right? So now I decided the curve. The curve was decided by W. So let's say that was a line, and beta is deciding how far I can predict using beta. Beta is the one, right? If beta is 0, then it means you are not allowed to deviate from the line. So for a given x, you are putting W into a function. That function is nothing but a line, right? And around the line, you have a Gaussian distribution because this is a mean. This is a mean, right? This is a mean. And how far you go away, it is a variance, which is given by the beta. So if you need to predict for this x, you take some random sample from this distribution, taking a mean here, right? So if you put some point, you will get some point nearby to it, right? If you are taking this x, the mean will be this. Using beta, you can take this, right? Or this can be this, but it comes from the Gaussian distribution. So it is a predictive distribution, right? So here I'm going to say that at first, when we were estimating using minimizing the log, like minimizing the sum of square error, we always had a one prediction for a given x, right? And that one prediction was a line, right? For this x, the only prediction we had was this when we were minimizing the sum of square error. But now, because we are using the probabilistic formulation, we can produce or predict any value of t around this point using the Gaussian distribution, right? So this is not a point estimate. This is a distribution I am predicting. I am predicting the distribution over a t. And once you are predicting a distribution over a t, you can pick any random point from that distribution. Clear? So there was a difference. At first, I was predicting only one point. Now I'm predicting a whole distribution. So out of the distribution, I can pick any point. Clear? Yes or no? Can you type quickly? Okay, fine. Good. Very good. Very nice. So this is very, very important and crucial to understand what is a point estimate and what is a distribution. So what is a predictive distribution? So you always have a clear picture in your mind that predictive distribution is a distribution over a target variables or over a target values, right? So based on the distribution, you can pick any value. Okay. So this somehow summarizes my first chapter regarding this, what we're going to do in another 5 or 10 lectures. I will quickly go over some terms that we will be frequently used in machine learning. One is model selection. So in model selection, as I told you, that there could be different orders of a function, a polynomial, which can fit to that data. Polynomial, it means to say that degree 1 can be fitted, degree 2, degree 3, degree 9, degree 20, any degree can be. How to choose which model is the best model, right? So what generally in practice in machine learning people do, they take a data set, they take whole data which is given to them, and they divide the data somewhere into 70-30%, right? 70% in 30%. Usually they do that, and 70% they fit to a model, right? In training, let's say now I have a though my data was like this, which was originated from the sinusoidal distribution. So when I fit a 9-degree polynomial, this is the curve that I'm going to get somewhere, right? Now I want to see like how good it is. So I take this 30% data here, which I have not used in training. And this 30% data somewhere come here, here, right? It may come here, here, and there, right? So now I want to predict. So though my original function was sinusoidal, if you remember, right? So for this x, I am predicting this value using my predictive function, but the true value is this. So there is a huge error, right? For this x, I am predicting this value from my function, but the true value is this. This is a huge error. So if this is the difference between the this is the testing error, right? Because I have not used this sample in training, and I'm just gauging how good my polynomial is doing for unseen data. So what I can do, I can take different models. For different models means I can take 3 polynomials, m equals to 1, m equals to 3, m equals to 9. And for all 3 m, I will find out what is my testing error. Whichever polynomial is giving the best testing error, I will choose that polynomial. Polynomial means I will choose that model, right? Sometimes ideally what people do, because once you find it out, like okay, m equals to 3 is doing good. So somewhere you are trying to overfit the data. How you are trying to overfit the data, testing data? Because you know now that if I take m equals to 3, my testing data will do good. So now you just, how do I get to know m equals to 3 was actually good? So somewhere people, what they do, rather than taking the 2 segments of a training data set, they take 3 segments. One is for training, other is for validation, and third is for testing. So they just use it for training. Then they compare it with that validation data set. And let's say out of 3 models, you found out that this second data set, just hold on. I'm in class. So this is a second data set which we will going to use it for like choose the model. Now this unspaired data set which we have never seen so far, using this one I have chosen like out of 3 models I have chosen amicus to 3. Now I will see further how this is doing good. So this is a testing data set. But in theory, no, but in practical we don't have huge data sets, so we don't divide these three segments, and generally we have these 2 segments only, training and validation. And sometimes people say validation as a test data set only, right? So it may be like interchangeably used in theory or in books, but mostly people divide, they take training and testing, and testing is just to validate how good I'm doing on unseen data set. There is one very common technique for model selection. If you don't want to waste your data, waste in the data means to say like if you are taking 70% only for training and data is so valuable that you are not seeing 30% and you have kept that for a testing purpose. It means you could have done better if you would have used 100% data set, right? But now because of your testing purpose, you have saved some 30% data. So that may like cost you much in terms of a data, because you have already less data, and in that less data you are only using 70% of it. So there is another technique known as cross validation. What they say, you just take your data set, divide it into some segments, right? So let's say for in this figure, the data set is divided into 4 small subsets, right? And you take once in one iteration or one run, you take these 3 subsets for training and use this subset for testing, right? Let's say you get 70% accuracy on testing data set here. Then you take these 3 subsets for training and use for this for testing. Here, let's say you get 60% accuracy on testing. Similarly, these 3 data sets for training and this for testing, and you get, let's say, 65% accuracy on testing data set. And similarly, these 3 for training and this for testing, and let's say you get 60%. You take an average and find it out how good you are doing on an average using the particular model. So by this way, you are not wasting, you are actually using every sample for training somewhere, right? But this the way that you do here is expensive in terms of training, right? If a neural network take 1 day to get trained, here by using this technique, you see there you have to run 4 times this same technique. So at least it will take 4 days or so. So it is expensive in terms of like training and just to find it out which one is good for model selection. But this is like a traditional technique which people have used it. Right? Simple. Am I connected? Can you just quickly say yes or no for it? Okay, so this is okay, fine. So some Yashdeep is asking, sir, for cross validation, as we are dividing into sets for training, so data should be more. No, we have taken a same data set which is provided to us, but now we have taken 4 subsets out of it, and out of 4 subsets we have taken 3 subsets for training, and we are doing iteratively for everybody.
So like for each subset, if you are training on a particular subset, so data for that particular subset should be more, no? Like if we
Data
just
for
have
particular
10, yeah, like if we just have 10 sample points and we are trying to divide it in 3 subsets,
right?
like
So it is
for a particular subset, the data should be more, right? Like if you are training on
no. So let's say you have 12 samples, right? Let's say
10
12 samples. So this is 1, 2, 3. So you are dividing into 4, right? So this is my first subset. 1, 2, 3. Second subset. 1, 2, 3. This is fourth subset, third subset, and this is fourth subset. So altogether, the data was provided to me was 12 samples, but I have divided into 4 subsets. Now I'm using 3 subsets at a time for training and 1 for testing, and I am doing it iteratively for every subset, right? So now for have 9 samples, and for testing, I have 3 samples every time. You got it?
Yes, sir. Yes, sir.
Okay, fine. Fine. Disadvantage, I've already told you that there is like the limitation here is computation, very expensive. Okay. Now, that's fine. What in the world if you do, if only likelihood estimation is given to you and somebody has asked you to choose the model, right? You have to do a model selection. And you know the better capability you take, the powerful model you take, it will always minimize your error and give you better likelihood, better probability or better likelihood, right? Best likelihood, I would say. So if your model is very, very powerful, then you will always get a zero error. And if you get a zero error, it means you always converge to overfitting. As I just told you that maximizing likelihood is nothing, but it is a minimizing of sum of error, which results into overfitting. So how to penalize, how to choose the model then? Because every time you just take a powerful model, that powerful model will always say that the probability, likelihood probability is better for the powerful model only. Then you always choose the model which is resulting to overfitting. So just to overcome that situation, what people have said that we can minimize the bias due to the likelihood estimation by penalizing the likelihood term, right? How we can penalize? We can penalize by the degree of the model, right? How powerful what is the complexity of a model? So if the m equals to 9, I'm subtracting 9. So it will somewhere I'm penalizing in terms of the model capability which I have used. So now at first I was choosing on this term, which was a log likelihood. Now I'm choosing the collective term here, where I'm penalizing the log likelihood estimation by the power of the model, right? So the bigger model, the bigger polynomial degree you will choose, the more negative it will go, right? If somebody have used 100-degree polynomial, and let's say if everybody get log likelihood is 10. So if somebody has used 100, so it is like 10 minus 100-degree polynomial is minus 90, right? Somebody has used 80-degree polynomial. So he may get minus 70, right? So it is minus 90 minus 70. Out of minus 90 minus 70, if you want to choose, you choose minus 70, right? So this is like you are penalizing in terms of M. And it is always preferred to a simple model. If you remember what we have done, what we have said that if you want to minimize the overfitting, what you can do, you can always walk towards the underfitting situation, right? And underfitting situation is nothing, that the complexity of a model is very, very less, even less than the true model, right? So it always, if you have 10 models and you want to go by this criteria, it will always choose the model which is very simple. And simple in terms, like if you have been provided m equals to 1, 3, and 9. So in this comparison, m equals to 1 is simple. If you have provided m equals to 0, 3, and 9, so m equals to 0 is simple here, right? Simple in that terms, which can explain data very easily. So there are multiple criteria to choose the models, out of which this is AIC, and where the likelihood is collectively put with the model complexity in terms of negativeness, and the total value which is maximized based on that, you will choose it, right? Okay. Now, if we are done with this, I want you to introduce with quickly the curse of dimensionality, which you will be seeing so many times in your career from now onwards, if you are going to land in data science or machine learning, deep learning. So let's understand like what is curse of dimensionality intuitively and how it matters really to us, right? So in simple sentences, the severe difficulty that can arise in spaces of many dimensions is sometimes as curse of dimensionality. It means to say that sometimes what we do in lower dimensions may not be good, may not be applicable in higher dimensions, and there the things goes wrong drastically. And because of those that mismatch, that mismatch between lower dimension and higher dimension, which comes here, that is known as curse of dimensionality. It comes because we have increased in dimensions, and the things that were applicable in lower dimensions are no more applicable in higher dimensions. Just to understand it, let's take a very simple example. Am I connected quickly? Just can you check me?
Yes, sir.
Yes, sir.
Okay, fine. So now I would just want to get your attention here in curse of dimensionality. Let's say I have these three colors here, blue, red, and green. I want to find it out. If I put this cross here, what color it will take or what class label it will take, right? So you can come up with different algorithms just to label this cross. Can you see this cross here?
Yes, sir.
This cross. Okay. So you want to label this cross, and based on your different algorithms, you can come up with different labeling. Just for the illustration purpose, we will take a very simple algorithm to label it. What author has said, let's divide this space into subspaces, equally subspaces, and then count the number of points falling into each subspace, particularly in which where this cross also falls out. And then we count all those major classes which fall into that particular subspace, and then we label that major class with the same label. We will give that same label to the cross also. You see this here. So what we have divided this two-dimension space into 16 squares, and out of this 16 dimension, this is the square where this cross falls, right? We will count all the samples here. Based on classes, we found out that the red one is having the maximum majority, and we will label this X as a red label, right? This is what this algorithm says. And in general, it is k nearest neighbor. If somewhere we will discuss it in some future. So this general algorithm, sometimes people put it into k nearest neighbor, right? We found out the nearest neighbor and then found it out like what is the major class there. So let's not go to that particular KNN, and we say that this is the simple algorithm what we have adopted to label this cross. That's fine. If I have 100 samples, right? Let's say I have some 1000 samples, and for each sample on an average, it is 1000 by 16 I will get on an average. What if, and because I want to always compare with the nearest neighbor which fall into the subspace, I need a good enough samples that should be there. It should not be that there I have a vacant space here and my cross is sitting here, right? If there is a vacant space, there is no data set from the training data, there is no sample from the training data set. I will never get to know what label I should give, right? It means every subspace should have enough number of samples so that I can decide what label to give to this cross. This problem is clear? Statement? Yes, no, quickly. Is this clear?
Yes, sir.
Okay, fine. Now see the cost, how the cost of dimensionality plays the role here. Let's say I had for dimension 1, right? I have 10 samples, right? If I have 10 or 12 samples, I want to divide it equally. On an average, I can get 3 samples here, right? For 1 dimensions. And let's say 3 samples are good enough to mark my cross. If cross falls in any of the subspace, I will find out the majority of the samples and just mark that cross as per the majority. Now, if I go from d equals to 1 to d equals to 2, how many samples I need in the same relativeness? Can anybody tell?
1.
Here I wanted, yeah, what is that?
So 1.
No, here I had 12 samples. So that when I segmented it on an average for every subspace, I have 3 samples, right? If I want to go for the same proportionality, how many samples do I need?
9, right? X1 into X2 effectively.
So see, each box got three samples, right? How many boxes are there here?
9.
So and
each
27.
27, right?
right.
And if I go for 3 dimension, how many samples I need for that so that each box gets 3 samples? 27 into 3, right? Total boxes are 27, 3, 3, 3. and each box gets should 3. So 27 into 3. So it will be 3 to the power 4. Yes?
Yes, sir.
Yeah. Right? So now you can see that as I grow in dimension, my requirement of samples are going exponentially, right? So the for the same task when I was needing only 12 samples, now I am needing 81 samples in 3 dimension. Getting 12 samples is easy, but getting 81 samples, and imagine if I have 100 dimensions, right? So it is 100 into the power 3 and then to the power, then multiplied by 3. So you can imagine like how it can go. Right? It can go exponentially like in demand. So this is the cause of dimension. You want to see in terms of like linear regression. So you remember we had used only one x as a univariate variable there for sinusoidal. Can you just nod your head yes or no in the terms? When we have created a data set for sinusoidal example, we had used only x as a univariate sample. Yes? Because x was this, and then we take the sinusoidal value and we did a noise here, right? So x was a univariate. X can take value from 0 to 1. The x was not a vector there. It was only a univariate variable which takes only one value between 0 to 1. Yes or no? Is it so? Am I connected, guys? Like you are not responding very
Yes,
quickly.
yes.
Yes, sir.
Yes, sir.
Fine. So now, if let's say, assume that rather than taking x as a univariate variable, what if I take x as a trivariate, right? There are 3 values, x1, x2, x3, and I want to take a degree 3 polynomial here. Say if I take a degree 3 polynomial in 3 dimension, then how many terms I will have? I will have first term which is having constant. Then I have all those 3 terms which is having only single variable x1, x2, x3. Then I have cross terms x1, x2, x2, x3, x3, x1. And then I have these tri terms x1, x2, x3, right? Only one. How many different terms can be possible? So the maximum terms, if you put it into a bit terms of big O, that can comes d to the power m, right? D to the power m, right? Because these are the cross terms which can be produced. And if you take the complexity, just ignore the lower terms and you just focus here on this term and put it in a big O term, then it is d to the power m, right? So these are the number of terms, and each term have a coefficient which you need to fit, right? So it means the number of coefficients which are unknown in terms of linear regression is growing exponentially here. And if they are growing exponentially, then you need that same proportionate data to fit this function, right? This is what the the information is trying to convey here. So if you are in high dimension and the degree of polynomial is also high, then the number of coefficients, undetermined coefficients, are d to the power m, and the number of coefficients, because of they are huge. To fit the data correctly, to get the good model, you need a good you need the proportionately well big enough data set, right? This is what the information here that is coming to. Fine. Any question on this slide? So I am trying to explain you the curse of dimensionality here. On this slide, I am showing you that when you were in univariate Gaussian, that was fine. Univariate variables, that was fine. But the moment you just proceed to high multivariate variables, x, where the x can have different dimensions, and you for bigger polynomials, m degree polynomials, then the undetermined coefficients in terms of w will be growing exponentially. To fit those undetermined coefficients, you need exponential data, right? So that is how your curse of dimensionality plays a role. So to get a bigger data, and that's a problem in machine learning. If the data is huge, then you don't need to fit a model, right? Every time you then come up with some KNN terms, and it will always give you a nearest neighbor, and then label can be taken from that approximate. So we don't have huge data. We have a less data and want to predict the model from that less data. Okay, so if there are no questions till this slide, then I will continue from the next class onward. Please let me know if there are any questions so far on this till this slide. At least type no questions if there are. So at least I got to know that you are not connected. They are connected. Okay. If there are no questions, please drop your attendance.